Okay, so as I said last time, today, unfortunately, I have to give this online version um, because I have to be at a conference. So first off, I apologize about that. Next, I have an announcement considering midterms, since some of you said you cannot attend midterms at the timeline that I suggested because you have to go to a conference. I've decided to have midterms as a take-home exam. So I'll make another announcement next week, but I will provide problems in PDF format on what day is it? The 24th. You will have roughly 5 days to solve the problems, and then you'll turn them in to my office, and I will grade those as your midterm. Okay? So, topics to cover today. I want to talk about perturbation theory, but before that, as always, I'm going to go over a recap of what we learned last time because some of the concepts might be rather dense. And the more you hear typically difficult concepts, the more you get used to it, and it helps your understanding in the long term. Okay? So, we're talking about how you can calculate these uh, the band structures of electrons in periodic structures. We went over this example of the chronic penny model. We saw that you can have energy gaps and energy bands, and this is related to what we see in an electronic band structure. So this is the model that we were looking at. We looked at periodic finite quantum wells, and we saw how you can solve this problem. But the math is a little difficult for you to solve and apply to actual atomic structures or solids. So therefore, we said we're going to try to solve this problem here, where we're going to start from a flatter regime. And we're going to pretend that if we add some potential here, how is that going to change this problem? So to do this, we first started off by solving this free electron model, where we don't have any potential at all. And the problem here was relatively simple. If you look at it, solving the problem itself, the mathematic framework was simple because this situation where you don't have any potential is something that you solved several times for when you were solving the infinite quantum well problem, the finite quantum well problem, and the chronic penny model. So the only difference is that in quantum well cases, we chose specific sets of eigenfunctions because we needed to satisfy boundary conditions. But here, there are no boundary conditions because, in a sense, it's completely free. There is no boundary that you need to satisfy. So then setting up the mathematical framework is straightforward, but then a problem occurs when you actually sit down and write the equation. This is my most general form of eigenfunctions. I can solve my differential equation and my eigenvalues come out to be this. But the problem is I don't know what K is. And in the past, we determined what K was by implementing boundary conditions to the problem. So because of this, we talked about this concept of what's called periodic boundary conditions. So instead of having boundaries at the edges of a system, we said that we're going to pretend that we connect the edges of the system together and assume that it repeats periodicity. So the strength of this technique is that I don't need to care really about the actual boundaries of this system. I just need to be careful about how often they repeat. What is their periodicity? So typically you can consider this as, for example, the size of your sample, the size of your crystal, and this implements boundary conditions like this that says, if I look at the wave function at a specific position here, it should be the same as if I moved my system here because it should repeat periodicity at this point. So if I write this in mathematical form, I get this equation where it says e to the ikl must be 1. And using Euler equation, that means that kl should be 2 n pi. And we saw that this allows us to determine the k values for our problem. Of course, if we actually apply this to a solid state system, instead of having an arbitrary L for the sample size, the better periodic metric to use is this actual lattice spacing of the solid A, and this is what we use. And therefore, if I were to write the energy, it allows us to write K in terms of 2 n pi over A, and that gives us the energy levels of a nearly free electron model. There was one other thing that you needed to consider, and that's that based on periodic repeating, I also have to have this curve that we just draw. Remember, this curve comes from this equation. You see it's quadratic in K. So that's all we're drawing here. But because my system is periodic, it has to repeat following Bravais lattice. Therefore, it should repeat in reciprocal space too. So since the units here are in reciprocal units of 1 over A, this means that this curve should also repeat every reciprocal lattice vector, because that was the definition of a Bravais lattice. It says I cannot distinguish between one point and the other if I were to shift by a Bravais lattice vector. Therefore, it's not that I have this single curve, I have all these curves that I need to consider. So because this makes the situation rather complicated to understand, people came up with this concept of the Brillouin zone, which is basically folding all this information back into this small space defined by one large vector K. So instead of having this entire diagram, I can draw all the electronic information in this small part here, which is called the Brillouin zone. And this information contains all the curves that are out here. Because for example, if I'm interested about this part, this is actually the same as this, because if I take this part and I shift it by K, this is the green curve that I get. This information, if I have this red curve and I shift it by minus K, I get this curve. This curve, again, is this curve shifted by 2K, and so on and so forth. So all the information that is inside this curve is actually inside this small region here, and this is why people study the Brillouin zone. So this concept was pretty straightforward in 1D, where it's easy to visualize stuff, but we saw that in 2D, it's not that straightforward. And this is because in one dimension, I only have one direction to consider, this translation of moving this curve by either plus or minus K. But in 2D, it becomes tricky because I can move it in this direction, which is the same as what I just did for 1D. But the problem is I also have vectors along directions like this, which is a combination of the two vectors. So because of this, it's rather not that straightforward to draw like this. And we saw that because of this, in 3D, it gets even more complicated, where I have to consider really complex shapes that look like stars and stuff. So to counter this, people came up with what's the best way to draw the Brillouin zone and contain information. And they figured out that they don't even need to draw this entire Brillouin zone region. You can focus all the information in this really small part. And this is thanks to symmetry, because if you look at this structure, you see that I repeat everything every 90-degree rotation I do. In other words, I can't really distinguish this point from this point, because if I took this plate and I threw it and I picked it up again, I look at it, I wouldn't be able to distinguish whether I was looking at this point, or this point. And because of that, even if I only have information about this small point here, it's equivalent to having information about these points. And if I also consider this mirror plane here, which is a reflection, I can't distinguish between this point and this point either. And thanks to that, if I fill reflections of this here, reflections of this here, and so on and so forth, I get this entire square region. So in other words, even if I just know the small properties of this small region here, in reality, I know all the important information I need to know about this entire region here. So the reason this is important is because we were just talking about the fact that it's not that simple to draw electronic band information in 2D or 3D, because I need to consider all these vectors, and I can't really represent it as simply as one dimension. But by doing this, I can define important directions. For example, I can define this direction, which is equivalent to these other four directions along this vector here. And then I can define another direction, for example, along this chain here. And this allows me to draw a diagram like this. So imagine what this means. It says that along this direction, from gamma to x, if I write these two positions here, what this curve is looking at is the energy evolution as I change my k vector from here to here. In other words, if I were to draw k vectors like this is the curve that I would get. On the other hand, if I look at this direction, if I draw k vectors like this that go from gamma to m, this is the type of evolution that I would get along this series of k vectors. So then if I know these two directions, the rest of this area I can draw by a sum of these two vectors, right? So if I have information like this, technically what it means is that I can calculate all the information in this small space, which gives me information about this entire Brillouin zone, which gives me information about the entire crystal. So people typically will draw electronic band structure like this. If you look online, if you look in your textbook, this is the type of electronic band structure that you will see. Of course, the letters used here are a little more complex because for 3D, there are different types of critical points. These are high symmetry points that denote these letters. But if you look up your crystal structure, for example, for FCC, these are the types of high symmetry points that you have. And you'll see that people have decided upon a set of rules that says, oh, if it's the origin, it's gamma. If it's the center of a face, it's called X. If it's the center of this face, it's called L, so on and so forth. So these lettering is not that complex. It's just something that you need to look up that's tabulated online. And it's a promise between everyone so that we can all be on the same page of communication. So using this information, let's actually look at an example of calculating band structure. So remember in the reduced zone scheme, when we were talking about putting everything inside the Brillouin zone, I want to fold everything back into the first Brillouin zone. So instead of only considering this, which would mean I'm looking at curves outside the Brillouin zone too, I'm folding everything back. I'm pushing this curve back using reciprocal lattice vectors k. So that's what this equation means. So instead of just considering this, I'm also considering the fact that I'm folding these vectors back in. And this is my original starting point. I'm looking at the vectors along this direction. Remember, this 2 pi over a comes from the fact that the periodic conditions that I'm using. And this is just a multiplier in between 0 and 1. And then I have all the reciprocal lattice vectors that I can fold back in to make this, to satisfy this equation. So if we actually follow this and consider that this is for an FCC crystal, I first look up the reciprocal lattice vectors for FCC. This is what I have. And then I know that for these HKL vectors, these HKL integers, we learned about as the Miller indices way back when we were first discussing Bravais lattice vectors and reciprocal lattice vectors. These are the lowest integer values that we can consider. Obviously, 0, 0, 0 will give me the lowest sum because it means this just becomes 0 and I just reduce to my simple equation form. Then I'll have 0, 1 bar 0, 1, 0, 0, 0, 0, 1, for so on and so forth. And I have these combinations. Of course, you have everything that follows after this. You'll have, 2, 1, 1, 3, 1, 1, so on and so forth, but we're just looking at the lowest ones. So if I plug this all in, I plug these numbers in here, I have all these vectors, I put that together here, I add this and actually take the square, I get the energy values that I can calculate. And if I do that, I get these numbers or integers normalized by the energy values of h bar squared over 2m at the points of gamma, which I've denoted as E gamma as u equals 0, and x, which I've denoted as when u is equal to 1. So I consider this, of course, if I draw the actual energy curves in between, this is what I get. I get this curve for the lowest curve here. I get these curves for these 4 states here, and I get these curves for these 4 states here. But what's important here is that because of this fact that I'm folding back different reciprocal lattice vectors into the Brillouin zone, it turns out that I have degeneracies. In other words, I have bands that have the exact same energy here. So these numbers here denote the number of bands that have the same energy. So this 1 means this is a single band that has no other bands with the same energy. This means I have four bands here that have the same energy, which is consistent with what we just calculated here. And again, here I have four bands that have the same energies uh, following these lattice vectors here. So if you look up band structure, as I said, this is the typical type of diagram that you'll find. As we saw, it follows directions along critical points of high symmetry points inside the crystal lattice. And as you see here, I have dots that denote the number of degeneracies inside the structure for each of these individual bands. So what's important here is that we're considering this for the free electron model. Remember our starting point. Our starting point here was this. This is the solution for a free electron model. This is something that we get from calculating this equation way back here, where I have my eigenvalues coming from the fact that I'm solving this equation. So if you look at this equation, it's a free electron problem. I don't have any additional potential. I'm just solving for the kinetic energy. Unfortunately, our actual crystal is not like that, right? We actually have potential. There is some potential V in addition to that kinetic energy for the free electron case. And because of that, as we've discussed several times up to this point, what happens is that there are some corrections to this free electron model. So for aluminum, for example, which is a real metal with real potential, you see that the band structure is slightly different. There are similarities. It actually looks pretty similar, but you see that some things happen here. Some gaps open up. The original energy levels are also slightly different. And the way you calculate this is using what's called perturbation theory. So as we went over near the end of last time, perturbation theory is a method to find an approximate solution by starting from the point where you know the exact solution for something. So it's actually a very useful tool, but it requires some quantum mechanical background for you to understand. So last time we went over those concepts. The key concepts were things like expectation values, orthogonality, this Braket notation, and then we talked about conjugate transporters, Hermitian operators, and we also talked about the similarities between functions and vectors. So we're going to go over those again in a step-by-step fashion, and then we're going to go on to perturbation theory. So expectation values said it gives us the probabilistic expected value of the result of a measurement. So in a way, this is what gives us the actual observables that we measure. So the expectation for energy is what we calculate if we're interested about the energy of a system. And the way you calculate it is that we put the operator that we want to calculate in the middle. So for energy, this would be H, the Hamiltonian operator. And we use specific states on each side. So if we're interested about the energy state of a specific eigenstate, for example, if I want to calculate the ground state energy, I put in the ground state eigenstate here, and I put in the complex conjugate of the ground state eigenstate, and I go through this integration for the Hamiltonian operator that would give me the expectation value for energy. So we went over examples here last time for position. We talked about this identity operator. So this is the wave function of the probability wave function of an electron. For me to find this electron inside this space, the probability is 1. So I use something called the identity operator. This is like 1 for an operator. So you can imagine 1 being in between this 2. This is following this definition of the expectation value. So if I calculate it, the expectation value of the probability of me finding this electron inside here is 1, therefore this should be 1, and that allows us to get this normalization constant A1. So similarly, if you were to calculate the expectation value of the position x, I'm just plugging an x here instead of 1. Now that I know what A1 is, I can actually calculate it, and you see that I get A over 2 as the expectation value of the position of the electron inside this quantum well for the ground state. Remember, this is the ground state wave function of the electron. So this makes sense because in the middle is where you'd expect the electron to be if I have this quantum well and I'm looking at the ground state. So this is just walking through the concept of expectation values and demonstrating that it actually makes sense if you sit down and calculate it. So then we're going to talk about this concept of orthogonality. This is something that you heard about probably in vector space and also when you learn Fourier transforms. Equation-wise, what it means is if I have two functions, or if I have two vectors, and I take the dot product, or if I multiply them and take the integration, if I get a value 0, this means that two functions or two vectors are orthogonal to each other. So this equation is useful because in math, we always want something to reduce to 0. But the other reason this is useful in quantum mechanics is that it turns out that eigenfunctions of a specific operator with distinct eigenvalues, they're automatically orthogonal to each other. This is a quantum mechanical principle. So this allows us to reduce the amount of math that we need to do when we go through quantum mechanics, as we'll see later on when we talk about perturbation theory. So these are just examples that determine or demonstrate that it's true. So if I compare the ground state and the first excited state inside this infinite quantum well, these are the eigenfunctions. And if I evaluate whether they're orthogonal or not, you see that, as we just said, the integral is 0, therefore they are orthogonal. So then we talked about this concept of bracket notation. It was named this way because this shape was called brackets. These parentheses are called brackets in English. And Paul Dirac decided that this is an easy way to walk through quantum mechanic algebra, as we'll see later on. And this is just another way of expressing what we learned before. So if you look at it, instead of writing everything as a function, I can write things like these brackets. And you see that if I had an initial state is a sum of 2, I can write it like this in Dirac notation. If I look at something like this, which is just this Hamiltonian operator operating on this state, I can break it up into 2, just like you would do for a function or a vector following this rule here. And this part is the same. If I were to close this side using this vector, again, I can just write it. Because I could write this vector as a sum of 2, this is equivalent to evaluating this. And again, we're going to use all these simple algebraic terms later on when we start deriving perturbation theory. So if I were to write the expectation value, this is how you would write it. If I want to evaluate the expectation value of this Hamiltonian with respect to these two states, this is how I would write it. It means this. Similarly, if I look at the projection of two vectors, this is me having an identity operator in between, because remember, 1 is the same as the identity operator in this terminology. And it would just mean that I take the integral of this state with itself, therefore I should get 1. If they're orthogonal, they should be 0. So this is just showing you that we can write all the things that we just learned in bracket notation, and it's more simpler. Instead of having to write all these integrals, I can just write them using these brackets. And because later on, as you see, when we calculate, there are so many 1s and 0s, this makes it much easier for us to walk through the math. So I also want to talk about this concept of conjugate transpose. Conjugate transpose is basically taking a vector, taking its transpose, and applying its complex conjugate. The important thing here is that if I want to go from a vector like this to a vector like this, so I'm switching the bra to a ket vector, I need to take the conjugate transpose. That's the only thing that you need to remember here. So similarly, you can do the same thing for a matrix. We're going to talk about why an operator looks like a matrix later on. But you see that if you take the conjugate transpose, which means that I take the complex conjugate here, and I take the transpose, which is switching rows with columns, there are certain cases where this operator is equal to its conjugate transpose, and we call these special cases Hermitian operators. And this is one small subtlety, because it turns out that all the physical quantities that we actually measure in real life, they turn out to be Hermitian operators. So things like we typically calculate in quantum mechanics, like momentum, energy, position, they're all Hermitian operators. So we're going to use this characteristic later on whenever we need to switch the position of the operator. But we're going to remember that anything that we are calculating now in this class must be a Hermitian operator. Therefore, they just keep the same form. I don't need to be careful about this conjugate transpose thing going on. But this is just a technicality that you have to remember. It's not always like this. This is special, and the cases that we're considering in class they all follow this rule because they are Hermitian operators. So these are examples of using this. So as I just said, if I want to switch this vector, this ket vector, to a bra vector, I need to apply a complex conjugate to this operator. But as I just said, since in class we're always talking about Hermitian operators, this is just equal to this, which is going to make our life easier. So then if I evaluate things like the eigenenergy of this Hamiltonian operator, this is the equation that I want to evaluate. I'm interested in calculating the expectation value of this Hamiltonian operator, which is going to give me the energy of the system. And I want to do it for this specific eigenstate psi e. But since this is an eigenstate, we know that this is equal to this because that's how an eigenstate, an eigenfunction is defined. And therefore, I can reduce this into this form. Since this is a constant, it just comes out front. It's no longer an operator, so it doesn't need to stay inside the integral. It can just come up front, and therefore I end up with this. This is just 1, therefore I get the energy. So we're going to use simple math like this a lot later on when we do perturbation theory. So as I said, finally, right before we start actually discussing perturbation theory, I want to go over this concept of functions and vectors because they're used oftentimes interchangeably in quantum mechanics, and I don't want you to be confused about why that's the case. So let's look at what a vector is. If you think about a vector, typically if you expand this concept to be larger than 3 dimensions, you can write it like this. So all a vector is, it's a list of information. I have coordinates for a certain component, and this is a list of those components. So mathematically, I can write it like this. It's a sum of some coefficients multiplied by the unit vectors for each of those components, or those degrees of freedom, right? So a function, if you think about it, it's really similar in the sense that a function is defined as a one-to-one correlation between 2 values. So x1 becomes fx1, x2 become fx2, so on and so forth. And this rule is what a function is. So if I write it, then fx is equal to a sum of all the fxn values here. But I can rewrite this as a certain coefficient times whatever entry I have here. So in a way, this looks really similar to this vector because it's just a set or list of information I have for specific coordinates or specific degrees of freedom. So mathematically, it turns out they behave the same because of this concept that they are both just lists of information. They behave really similar when you try to manipulate them. And you can consider a function to be roughly a vector with infinitely many components. So in quantum mechanics, we're going to use this property to manipulate functions like vectors. So if you ever see functions, me using the word function, but they mathematically, I'm using vectors to go through the math. This is why I'm just considering functions like vectors. So if I say eigenfunctions, but I'm just using vectors, it's because they're very similar, and mathematically it doesn't make a difference really when you write them down, and it's easier to work with vectors following the Dirac notation that we have earlier. Okay. So I want to walk you through a concrete example so you get less confused. So remember this problem for the infinite quantum well. We saw that eigenfunctions have this form, right? This is general. I have a specific coefficient, then I have sine kx, and k was equal to n pi over a, and n could be 1, 2, 3. This was quantum mechanics, right? And 1 would look like this, and 2 would look like this, and 3 would have 3 nodes, and so on and so forth. So we're going from the ground state to higher and higher energies as k increases, right? So if I define this function, base function, to look like this, which is just a different version of this, I'm just using n as my indicator instead of k. In general, I can write this function as a sum of all these n's, because a general solution to this problem, which is a differential equation, if you remember where it came from, the general solution can be written as a linear combination of all the other solutions that I have. Therefore, I can, in general, write this equation like this. But at the same time, it satisfies this condition. So this is a Kronecker delta, which means that if m and n are equal, it's equal to 1. If m and n are different, they're equal to 0. And this comes from the orthogonality argument that we had before for eigenfunctions of a specific operator. So if I write this in bracket notation instead of function notation, so I'm transforming now from functions to vectors, I can write it like this. Because I can treat these like unit vectors, and I can treat this as coordinates for these vectors, then my general eigenvector of this problem will be a sum of smaller vectors like this. So we did this for the infinite quantum Well case, but as I said earlier, the concept of going from functions to vectors is rather general. So we can do this for an arbitrary solution in quantum mechanics. So because of that, what we're going to do from now on is that when we write a general solution for a quantum mechanical problem, we're just going to write it always like this. It's going to be a sum of all the eigenfunctions, all the other smaller general solutions that we have for it, and I'm going to have an arbitrary constant in front of it and write it like this. And this n is going to be the nth eigenfunction or eigenvector. So this is nothing more than us following terminology like this, and we're just applying it to more complex problems. Okay? So then you should ask, what are operators? Because, okay, I can be a little convinced that functions are just like vectors. They're just lists of information. I understand what you're saying here. Okay, I'm okay with you writing eigenfunctions in this form. But what about operators? How are these written in vector form? So if you think about what an operator does, it's transforming this vector, right? This is just a sum of these are just the coefficients here, Cn, that are being written here, A, B, C, D, E. If you think about what this does, it's not changing the size of the vector. It's just changing the coefficients for each of these components. So if you think about what does that, it's a matrix. So if I have a matrix multiplying a vector here, it's going to give me another vector with different types of coefficients, just like this, right? If I were to write it like this. So what this means is that I can write this operator in the form of a matrix, and I can write this new vector. If you look at it, it's just change the coefficients of the vector. It's not changing the size of the vector, and it's not changing anything else to the system. I'm just changing what I multiply in front. In other words, I'm going from what looks like this to this. You notice that I have a C prime here. So what this means is that even if I have a new state, if I had an old state and I applied an operator to it, then we changed it. Remember things like translation or inversion, we're changing the entire vector. But even if we do that, I can use the same basis. So this word basis, if you remember what is for vectors, it's the XYZ coordinates, for example. It's if I have in 3D space, my bases are the XYZ axes. Here, my bases are the eigenvectors here. So I'm using the same basis, I'm just modifying the coefficients here. So again, we're going to use this principle to make calculations easier when we walk through a perturbation theory, okay? So finally, we're ready to approach perturbation theory. So the concepts earlier, even if you don't fully understand them now, just assume that they are true because that's what's important when you actually try to solve this problem of perturbation theory. Okay, if you're interested, look up quantum mechanics text. There's a lot of good lectures out there that go through quantum mechanics in gory detail. I can suggest them. If you're interested, send me an email and I will guide you to some really good videos or textbooks that can walk you through all those basic concepts very carefully. Okay. So the statement of the problem for perturbation theory is that I want to solve this problem for a general Hamiltonian, but I'm starting from somewhere there. I know the exact answer for a simpler problem, and then I got to add a small modification to it and see if I can solve it. I want to approach the problem and try to solve that problem starting from my simpler starting point. So mathematically, if I write it out, this is what it would look like. So this is the Hamiltonian that we want to solve. This is the Hamiltonian that we know the exact solutions for. So for example, this would be the free electron problem. We know the exact solutions for the problem. But then since this is the Hamiltonian that we actually want to solve, there's going to be a small correction to it. So this delta H is the additional operator term for everything else. And then I'm going to have a small constant multiplier here, lambda in front. And this is important because this allows us to approach this problem mathematically. We're going to start from the point when lambda is very, very small, or lambda is 0, and then we're going to start increasing lambda and see what happens. Okay? So this is the problem as I just said. So since when lambda is 0, we don't have this term. So we know the exact solution for this H0. So we know the exact energy levels here. We know where they are. And the question is, what happens as we turn on this delta H? In other words, what happens as we slowly start to increase lambda from 0? So anything can happen. It could evolve like this. It could evolve like this. It could evolve like this. But we want to know how we can approach this problem and how we can get these energy levels because as I said last time, many of the problems in quantum mechanics, they're not easily solvable. They're not exactly solvable. So we're going to use this approach to try to get these energy values, and that's going to give us some information about the system. So depending on the situation that we start, there are two types of perturbation theory. There's something called non-degenerate perturbation theory. Remember what degeneracy was. It was whether I have other states with the same energy. So this non-degenerate perturbation theory corresponds to this case, in this case, for example, where I start off from one state, I don't have anything that's degenerate with it, and I'm solving perturbation theory for that situation. Then we also have what's called degenerate perturbation theory. This starts from a degenerate situation where I have at least two states that I have the same energy. And then I'm going to solve the problem here and see how that changes the problem. Later on, we'll see why you need to divide it into these two situations. But for now, just assume that I have something called non-degenerate perturbation theory, and then I have something called degenerate perturbation theory. Okay? So our starting point is here. We want to solve this problem. So let's start from what we already know. What we know already is that we know all the answers for this because we know how to exactly solve this problem, right? So if I write that out mathematically, this is what we know. In other words, for this operator, HO, I know all the eigenstates are. I know that they have multiple eigenstates, so I'm going to call them kth eigenstate. This is just an integer. It could be my first eigenstate, second eigenstate, third eigenstate, so on and so forth, just like for the infinite quantum wall problem. And then I have this 0 as a superscript here because just to denote that these eigenstates are coming from this operator, this H0 operator. So I have this huge 0 here, okay? Since I know these eigenstates and I know the exact solutions here, I know what the exact eigenvalues are. So these are my eigenvalues E. Again, I'm using K as a subscript for the kth eigenstate. So remember, for our infinite quantum wall problem, I had solutions for the first eigenstate, the second eigenstate, the third eigenstate, so on and so forth. So that's the number here. And again, this 0 is just denoting the fact that this is an eigenstate for this operator, the starting Hamiltonian that we already know the answer for, okay? So this is just going through terminology of what these things mean. We also know that this holds. Remember what we said about orthogonality earlier. For an eigen for eigenfunctions of the same operator, if they have different energy, it turns out that they are orthogonal. So orthogonal means that if I take this, which is equal to this, remember, following direct notation, I should get this Kronecker delta. In other words, if these two eigenstates are the same, I get one. If they're different, they're zero. And this word means orthonormal means it's just orthogonal plus normalized. So it's orthogonal because if I take two different eigenstates, it's zero. It's normalized because if I take the same eigenstates, it's not an arbitrary constant. It's defined so that the arbitrary constants are defined so that it's exactly one. So what this means is, remember when we were talking about this value a in front, when we were talking about this state, instead of having an arbitrary number, it's already designed its factor in so that the final answer that I get is always going to be one. Okay. So this is the first piece of information that we know. The second piece is, since we're talking about non-degenerate perturbation theory, I don't have any degeneracies. In other words, I don't have two states that have the same energy, which means that they have to go in this order. My lowest energy state, my second lowest energy state, my third lowest energy state, so on and so forth. There are no cases where they are exactly the same. So keeping this in mind, this is the problem that we want to solve, right? This is what we actually want to solve. And these are the answers that we're aiming to get. I want to know the answer. I want to know the eigenstates and the eigenvalues for this Hamiltonian operator, which is a function of lambda because it's going to depend on what the size of lambda is. I'm going to have my eigenstates. They're going to be, first eigenstate, second eigenstate, third eigenstate for this operator. So that's why I'm using this letter n here. Those are also going to be a function of lambda. And then I'm going to also have an energy, En, which is also going to be a function of lambda, right? So what's important here is that if lambda is zero, this reduces to this, right? So if lambda is zero, I should recover the solutions I already know for H0. So what this means is if lambda is zero, this is equal to this. Remember our definition earlier. And this should be equal to this. So based on this characteristic, I should have a continuous change. In other words, starting from lambda is zero to where I am now, I can't have a drastic change. I can't have an abrupt change because in physics that can't happen. I want to have a smooth transition. So what this means is that I can write a perturbative series. In other words, I can approximate something like a Taylor series so that I can smoothly connect this point when lambda is zero to points when lambda is not zero. And when lambda is very, very small, I'm going to approximate it like Taylor series. So this is what I mean by that equation. I'm going to write out my correction. This is my general solution as a function of lambda. But my starting point is going to be n0, the solution I already know. And there's going to be a first order correction. There's going to be a second order correction, so on and so forth. Same thing with my energy. I have my starting point, which is the energy when lambda equals zero. This is what we already know. This is for this case. And then I have a first order correction to energy and a second order correction to energy, and so on and so forth. So in a way, this is the key idea of perturbation theory. It's just an approximate method to solve this problem when lambda is small. And I'm going to start from this point, and just like Taylor series, when you learn that for functions, we're doing this for states, we're doing this for eigenstates or eigenvectors, and I'm trying to figure out what my approximate solution would be by adding first, second, or third order corrections. Just like in Taylor series, the more order corrections you add, the more accurate you get. That's the same thing is going to happen here. The more order corrections that I get, the more closer I get to the actual answer. And the degree of correction is typically higher, the higher order corrections you have. So because of that, people will typically consider up to second order corrections because that already gives you a lot of information, and it gets harder and harder to calculate more and more order corrections, as we'll see shortly. But anyway, this is the key idea of perturbation theory. So if you're going to remember one thing, this is what you should remember. It's that perturbation theory is nothing more than just something like Taylor series to this Hamiltonian solving problem. And I'm trying to get an approximate solution using this framework. Okay? So if we look at this equation, the unknowns that we have are here. Lambda is a tuning parameter. I'm determining whether the size of what lambda is, but these are the unknowns that I have. I don't know what n1 is. I don't know what n2 is. I don't know what en1 is. I don't know what en2 is. And in a way, these are what we're looking for. I'm curious about what my first order correction to the vector is, what my first order correction is to the eigenstate, and I'm curious what my first order correction to energy is, okay? So we're going to write out the entire equation now and see how, if there is a way that we can calculate these unknowns. Okay, so this is just the equation that we're trying to solve. This is our eigenfunction equation that we're trying to solve. This is just the new Hamiltonian. This is the eigenstate that we're trying to solve. I can rearrange this. I'm just pushing this to the left side here. This is what I get. And then I'm going to plug in here this expression. So instead of using n lambda, I'm going to write it out like this. And instead of using en lambda, I'm going to write it out like this. So that's what I'm doing here. Instead of using n lambda, I've written out as n0 plus lambda n1 plus lambda squared n2, so on and so forth. Instead of writing en, I'm writing them out as all the orders. So what's important here, though, is that if I want this to be a general equation, this equation has to be satisfied for all lambda. It's not being satisfied for a specific lambda. It's being satisfied for all lambda. So the only way that can be true is that I need every order lambda for nth order lambda to be zero. So what this means is, for example, for lambda order zero, when I only have constants here, the only term I have is this multiplied by this. That means this term must be zero for this equation to be true for all lambda. If you look at it, this is what we already know, because if you look at this equation, all this is, it's the original equation. It's the equation that we know for the Hamiltonian that we already know the exact solutions for. So then I look at first order lambda, I have this multiplied by this. And then I have this multiplied by this. That's going to give me first order lambda, right? So that's what I write here. Again, for this to be true for all lambda, I need this equation to be satisfied. It's just sending this over to the right side because it's a minus, and you see that this has to be true. So then I can do this for kth order, second order, third order, so on and so forth. If I write the general equation, it's going to look like this. I start from k order here, and I have to go down consecutively in one by one, all the way down to n equal here, to zero here. So what this means is that I can solve this equation recursively, which means I solve this equation first, then I can solve second order, then I can solve third order, and then I can solve fourth order, so on and so forth. So let's see how you can actually do that. So this is our starting point. This is our first order equation here that we want to solve. And this is where we're going to start using this bracket notation that we talked about last time and earlier today, okay? So the first thing that I want to do here is that I'm going to multiply this bra vector n0 on both sides. So I'm going to multiply it here, and I'm going to multiply it here. Because I have this equation, me multiplying two of the same vectors on each side doesn't change this equation, right? It's just this equal sign is going to hold. So that's what I'm doing here. So this is the result that I have. But then I'm going to break this apart into two parts and see how I can solve this equation easier. Because what I know is that this n0 is an eigenstate of this operator, right? So I can rewrite this like this, right? Because this is nothing more than the eigenvalue, eigenfunction equation that we've solved so many times. It's just written in a different form following Dirac notation. I have this vector on one side and the other, but this is just a terminology thing. It's not changing any of the equation itself. So then if I include the next term, it turns out that since this has changed into this, inside here, it's just this minus this. Because these two are constants, this is zero. So what this means is that I don't really need to care about this part. Whatever this is, it doesn't matter because the moment I multiply this vector on the left side here, this entire term becomes zero. So what this means is that this must be zero. And this is important because this already gives us information about this first order energy correction. So let's look at that here. So again, let's look at it step by step. So I can break this into parts where I evaluate the expectation value of this first and then this. So this first part, this is a constant, so it comes up front, it becomes this, and then I'm just need to evaluate this and this. And this is one, remember, following orthonormality, this was given as one because this is already a vector that we know. And this side I need to actually evaluate I actually need to evaluate the expectation value of this entire thing because I don't know exactly what this Hamiltonian is, right? But this is interesting because what this equation says is that if I then take this to the left side here, this is the result that I get. Look at what it says. It says my first order correction. Remember what this term was. This was the first order energy correction here, which came from this equation here. My first order energy correction is equal to the expectation value of the correction to the Hamiltonian. This is the addition part to the Hamiltonian. Remember, this comes from here. It's the new part of the Hamiltonian, the correction that we're adding. The first order energy correction is the expectation value of the additional Hamiltonian part with respect to the original states, the original eigenstates. These are the original eigenstates, okay? And we can calculate this. This is just a matter of plugging things in because we know what the eigenstates are for the problem that we can solve. That's what we're going to put here. Then we know what the correction to the initial Hamiltonian was. In other words, it's our potential, for example. I plug it in, and if I calculate the integration, that gives me the first order correction energy to the system. So this is important because for this first order correction of energy, I didn't need to know the corrected states. I didn't need to know the corrected eigenstates. So this is really useful because typically, as we'll see in the next few slides, calculating the corrected states is a lot more complicated compared to calculating the corrected energy thanks to this. So this was for the first order energy correction. So let's see what happens when I try to, if I want to make my calculation more accurate, if I want to calculate higher order energy corrections to the system, let's see what we need to do. So we're following the same logic here. I want to then now look for kth order correction. So remember the equation looks a little different here on the top. This is because, remember, it comes from this. I'm looking at kth order lambda and I'm making everything the same. This is more complicated because now I need to consider these lambda multiplications that give me kth order lambda. That's going to give me this equation that needs to be satisfied. But if you look at it, the left side is the same because the moment I multiply this, what happens is that this reduces to this, and therefore this term always becomes zero. So this left term, the moment I multiply this, always becomes zero. And then I just need to evaluate this side. So then if I start looking at this side, it turns out that also a lot of terms become zero because I'm going to use orthonormality. What this means is that if I have a case where I have a constant, like I have here in these later terms, if the vectors are not the same, they're all going to reduce to zero thanks to orthonormality. The only case that survives is this, when I have this vector reduced all the way down to zeroth order. So if you look at this, this is going to be when I have order k here, right? because then k minus k is going to be equal to 0, and that's going to give me my state, and I have ek here. So this is the only term that's going to survive. Here, in the first part of the equation where I have both terms, again, this term dies because of the same rules here. This is the only part that's going to survive. So in the end, once I multiply this on both sides using bracket notation, and then considering orthonormality, this is the only thing that survives. So again, look at what this equation says. It says the kth order correction to energy can be written like this. It looks exactly, in a way, the same as our result here if you compare it. The only difference is what's here on the right side. Here, we were looking at the expectation value of the additional Hamiltonian with respect to the ground state on both sides. Here, it's the same up to here, but what's different is here. I need to know the corrected state for k minus 1 for me to be able to solve the kth order correction. And again, if I put 1 here, for example, so that I can know the first order correction, the equation still makes sense because then this becomes 0, and that's the exact same equation as we saw here. The problem here now is that if I want to know the kth order correction, I need to know the k minus 1 order correction to the eigenstate. And this is something that we now need to learn how to calculate, okay? So to calculate this, I need to know how you're going to calculate the kth order correction to the eigenstate. So the framework is always going to be similar. We're going to start from equations that we know. We're going to try multiplying other types of vectors on this equation and see what we can get, okay? So here, what we're going to do is we're going to multiply this time a k0 vector on both. So remember what this means. It means I'm using an eigenstate for the original Hamiltonian. It's just not going to be the same eigenstate as before. So this nk were just integers of the original Hamiltonian. So this could be the first for example, if this was the first eigenstate of the original Hamiltonian, this is going to be the second eigenstate of the original Hamiltonian, okay? So then let's see what happens. I multiply it on both sides. Remember, in the past, what had happened is that since this is an eigenstate, I can write it like this, but then these two were the same and they became 0. Now they're not the same because I'm using a different eigenstate of the original Hamiltonian. So I just get this equation. I get ek0 minus en0, and I get this projection of this vector onto this. That's going to be equal to what I have here on the right side. Okay, so instead of 0 on the left side, I now actually have a term because I'm using a different vector of the original. I'm using a different eigenvector of the original Hamiltonian. So now let's evaluate this right side here. So I'm plugging everything in here. Here, again, what I'm using here is orthonormality because I have a different vector. If I have different types of eigen vectors here, orthonormality says that since this is a constant, I get a 0 value. And I get this term again here, where I'm saying I'm taking the expectation value of this corrected Hamiltonian with respect to nth eigenstate of the original Hamiltonian and the kth eigenstate of the original Hamiltonian. So to save space, we're not going to write this fully like this anymore. We're just going to write it like this. I'm going to write delta H, and then I'm going to have two subscripts here in order. So if I have Kn, it means I'm taking the expectation value of this additional Hamiltonian with vector K and vector N, okay? So if I summarize this entirely, then remember we had this on the left side, and I have this on the right side. I'm going to divide this on both sides. That's going to give me this final equation, right? It says the expectation value of the identity with this original K vector of the original Hamiltonian and this first order corrected vector is equal to this. That's what this equation says. And this shows us why we need to be careful about degenerate and non-degenerate cases. Okay, remember what degeneracy means. It means I can have the same energy even for two different states. That was what degeneracy meant. So if we see here, if n and k, for example, are different states, but they have the same energy, this energy would be equal to this, then this would become zero, and this term would be ill-defined. I can't mathematically define it because it would diverge. So what that means is that we can't use this framework for degenerate perturbation theory because this entire equation would break down. But remember, for non-degenerate perturbation theory, we already assumed that there will never be cases like that. We already assumed that this condition is met. In other words, En can never be equal to Ek. So we are safe to use this equation here. Okay? So this is actually gives us really important information because this is just like the projection of one vector on the other. It gives us the vector component of n1 in the k0 direction. So if I do this for the k direction, for the k eigenvector, for the L eigenvector, for the M eigenvector, for the original Hamiltonian, I can get all the components in all the directions because remember, we can write a vector as a sum of all the unit vectors or all the eigenstates with a specific coefficient multiplied in front. This just gives me the projection of this vector, or it just gives me this coefficient in the kth vector, for example, because everything else is going to be orthonormal. They're going to die out. The only term that's going to survive is going to be this k vector. Therefore, it gives me the coefficients in each direction. And what this equation then says is that this value that I have here, this is just this coefficient in this direction. So if I write this mathematically, it says my first order corrected state is nothing more than a sum of all the eigenvectors in the original Hamiltonian, but the constants that we have in front of them are going to be defined by this. So this equation, this formulation, it gives us information about the first order corrected vector, okay? So now we can calculate the second order correction to energy because if following this equation for the kth order correction for energy, if I put in 2 here, it gives me this equation. We just calculated what n1 was. It's this. So I plug it in. This is what I get. I guess I'm missing a delta Hn here. And I can rewrite this equation like this. So it gives us a clean expression of, again, how I can get the first and second order corrections using perturbation theory. So this was great because it gives us information about, for example, how we're going to calculate these terms here. It allows us to know that I'm looking at how this would evaluate. We're calculating how this would change. And we just calculated how I can get it for first order correction and even up to second order correction in energy. So that would give us a pretty accurate approximation. Because remember, for Taylor expansion, if you take the first and second terms, it already gives you a pretty nice approximation to the curve that you're looking at. And similarly, as long as lambda is small, as long as I'm looking at a small correction compared to the initial Hamiltonian, my results should be pretty accurate because I'm considering up to second order. So that was great, but the problem is, if I start looking at second order correction, we had this problem. Remember, if I had a degenerate case, if there was ever a case where the n state energy and the kth state energy are the same, this would be zero, this would diverge, and I no longer can really talk about what the energy correction would be. So because of this, we need to consider this separate case for degenerate systems, which is called degenerate perturbation theory. Okay, so as I just said, this is what's different from before. Everything else is the same. We're using all the information that we previously know for the original system. The only difference now is that there is coincidentally one case or more where these two different eigenstates, m and n plus 1, or n and k, whatever, they turn out to have the same energy. So that means these expressions that we derived for the second order correction energy, for example, or the first order corrected state, I can't mathematically define them anymore. So I need to figure something out. But you might think, for first order, it doesn't matter. I looked at this equation, it looks fine. I don't need to worry about anything because nothing is divergent, nothing is mathematically defined. Does that mean I can use the same expression for first order? On surface, it looks okay, but in reality, it's not. And here's why. So let's trace back at how we got this result. Remember what we did is we multiplied n0 on this side. And what that allows us to do was that this transitions to this because this is an eigenstate of this operator. Therefore, it's just a number in front. And then I'm going to write it like this, and this becomes 0. The only problem now is that because I have a degenerate possibility, because I have another situation where this can be 0, because the energies are the same, I need to also consider the case for k0. So in other words, if I apply k0 on this side here, I get the same results because ek is equal to en here, and therefore this term also becomes 0. And I need to consider how this affects the problem because if you look at the right side here, this is clearly different from this where I have k on the left side, but I need to simultaneously consider this so that I can properly solve the problem. So the proper way to do this is that I'm now going to multiply something that looks like this on both sides instead of multiplying them independently. So I'm going to multiply a sum of these two vectors. I don't know what these coefficients are, but I'm going to multiply them together on the left side and right side here and then see what happens. So if we walk through what happens, on the left side, obviously, it's still going to be 0 because this was 0 and this was 0. So they're both 0. So I'm not going to write that out. On the right side here, we're going to consider everything. So the first case for n, you see this is a constant. It'll survive. But then when I multiply k, this is a different eigenstate. So therefore, they're orthogonal to each other. So I get 0 here. And then both of these terms will survive, right? Because this is just an additional operator, and it survives for both this case and this case. So this is the equation that I have. So if I write it out, it's going to look like this. And this is one equation that I have. At the same time, I'm also going to consider it when I change this n and this n to k. Because the energies are the same, the left side gives me the same result. When I multiply this, it's still going to be 0. And the right side is going to give me different information. So if you look at it, it's only reversed here. So this time, since n0 and k0, they're different vectors, this gives me 0. But this time, k is equal to k. So this C2 term will survive. So this is the equation that I get. And I'm going to rewrite it like this. So this says I have two equations for two unknowns, C1 and C2. And I'm going to use this to solve simultaneously. So I'm going to solve these two equations simultaneously. And for now, I'm going to assume, for simplicity, that Ek is equal to E. In other words, this corrected energy is the same because we started off from the same point. And there's going to be a small correction. So I'm just going to treat them the same for now and then see what happens. Okay? Coming back here, I want to solve this equation for C1 and C2. I can write it in matrix form like this. And this is me just writing this equation in matrix form. And we're going to use typically what we always use for equations like this, for series equations, for this to be a non-trivial answer. In other words, for this equation not to be the simple solution where C1 is equal to C2 is equal to 0, which is a trivial solution, it's useless. I need the determinant of this matrix to be 0. Because if not, what's going to happen is that I take the inverse matrix of this, therefore C1, C2 is equal to 0. So to avoid that, I need the determinant of this matrix to be 0, and that's going to give me my energy. So I need this determinant to be 0. So then I need this to be 0. And since now, as I said, compared to here and here, the main difference is that right now I'm assuming that this is the case. So I'm rewriting EKN as EN here. This is a roots equation that you should know all how to solve. This is something that you learn in middle school. I'm solving for this. The rest are just some constants that you can calculate, these expectation values that you can calculate. And this is the solution that I get for the roots equation. This gives me what my first order corrected energy solution is. So this is your formal solution. It has a plus minus here because one is going to be for the En and the other is going to be for the Ek. Even though we assume that they were the same, they're slightly different. That's going to give me this energy splitting. Typically, if you look online for textbooks, for example, in Ashcroft and Merman or Kittel, for example, you'll see that this expectation value, even though we don't know what it is, just to give you better understanding about the physics, mathematically, they define this as 0, which really simplifies this equation. The only term that stays behind is this term. So everything else here becomes 0. This is the only term that survives. So then the first order correction then just becomes plus minus absolute value, delta H and K. Remember, this is the expectation value of this Hamiltonian with respect to these two vectors here. So this is our answer. This is what you get. So if we had a degenerate point here, if I apply first order degenerate perturbation theory, it turns out that this degenerate point, the energy splits into plus delta H and K and minus delta H and K. Therefore, a gap opens up, a band gap opens up. And the size of this band gap is going to be delta H and K. So this is exactly what's happening when we talked about this. When we had this free electron model, everything was just simple lines, and they had these cross points where I had multiple values. What degenerate perturbation theory says is that if I now consider this delta H, which is the potential of the actual lattice, since I'm not solving for a free electron, I need to actually consider that potential of the lattice. If I include that, I'm going to have a certain expectation value associated with that potential for the two eigenstates that make this crossing. That's going to open up a gap with a size of 2 delta H and K, and that's going to give me this band structure. Same thing is going to happen here. Of course, now the types of vectors that give me this are going to be different, so the values are going to be different. So the band gap openings are different at each of these degenerate points. But this is what allows you to get to remember that aluminum band diagram that we saw in comparison with the free electron model. Remember way back when we were talking about this, these gaps opening up, this is where they come from. Since I now consider the potential of aluminum, it's a certain addition to the free electron case. That addition will have a certain expectation value with the vectors that make this crossing, and that's going to open up this gap. And the size of the gap is different for each crossing because I have different eigenstates crossing, and I have a certain potential associated with that crossing. So if we look at an actual example here, mathematically, remember, this expectation value was an integral like this. It's looking at the integral of this state K of the original eigenstate of this free electron model and this other state N of the free electron model with this corrected potential, this correction, this addition to the potential. If we actually apply that to our free electron model, remember for our free electron, this is what our eigenstates were. Our eigenstates were what order reciprocal lattice vector I'm folding in. Remember, this is folding in vector -1 because I'm folding in a curve that should continue like this. I'm folding it in by -1. That's going to give me this line. And this curve is the original curve when n is equal to 0. So I can write in general all my eigenfunctions like this. It's going to depend on k, which is just in between here and here. And it's also going to depend on a, which vector I'm folding in. As we just said, this is folding in this curve by minus reciprocal lattice vector 1. This is folding this line in by plus 1, so on and so forth. If we have higher order crossings here, that's going to happen. So here, for example, the two eigenfunctions that are crossing, in other words, this function and this function, are actually this, which is this line, right? Which I can write like this, and this line, which I can write like this, because remember, I'm folding this line by minus 1 vector here. That's going to give me this. And then I can write this gap opening size, or half of the gap, because I need to multiply 2 to get this actual gap size. This is how I'd calculate it. So if you look at it, this is what I meant. The value of the gap is going to depend on two things. It's going to depend on this additional operator, on the potential that we're adding to the system. And it's going to depend on the types of curves that I'm crossing here. For example, here it's 0, 1. This is 1 and minus 1 crossing, and so on and so forth. So this delta H for the nearly free electron model is this Vx. So again, remember way back, this correction, what it is, what this delta H is, compared to the free electron model and the nearly free electron model, is we're going from here to here. So the small addition in potential is this V0. It's going to be a function of position, right? It's a function of x because it repeats every so on and so forth, and it's going to have a certain profile. And we're going to include that in this delta H. We're going to write this as a certain potential. So I can write it as function Vx. So if I rewrite this equation, I can write it like this. It's a function of position. The potential is a function of position. And these e to the ik x's, in reality, what's only important is the difference between these two vectors. So it's the delta kx I have here. So it turns out this gap is going to depend on this. It's going to depend on the crossing, which vectors are crossing, what's the difference between the reciprocal lattice vectors required for shifting this in, and it's also going to depend on the potential. And coincidentally, this is the Fourier component of this potential. So this is another reason why Fourier decomposition, you learn it in engineering mathematics, because it turns out it's related to all the actual physical properties that you see. If I perform Fourier analysis on this potential, it's going to give me information about these band gaps, even if I didn't intend on it, okay? So this is how perturbation theory works. Again, you don't need to exactly understand the entire framework of how this works, but this course is designed so that I can introduce you to the concept and you know where this band gap opening comes from. It's coming from this small correction from this additional potential. And you know how to calculate it because if we walk through the actual math, it turns out it's the results, the actual energy corrections aren't that complex. And they make sense because if I have a larger potential here, it's going to give me a larger correction. Depending on the overlap here, it's going to give me different types of openings. And that's why the band gap values that you see in actual band structures are actually quite different. Okay. So this is the end of the lecture or the course before midterms. So midterms will contain problems up to perturbation theory. So sit down and actually study them. If only the slides are a little difficult for you to understand, I suggest reading texts like Ashcroft and Merman. Or if you send me an email, I can probably guide you to other basic quantum mechanical videos that will introduce you in more detail to the concept. Okay, so as I said at the very beginning of the class, instead of having midterms in person, which was what I initially wanted to do, some of you have a scheduling conflict. So I've decided to have midterms as a take-home exam. You will have roughly 1 week to solve the problems. I will hand them out on the 24th. You will hand them in by midnight on the 30th. I typically don't suggest that you work together. You can if you want, but make sure to write the answers on your own. If you fully copy another person's answer, I will give you 0 points. So don't do that. Even if you work together on how to solve the problem, write the final answer and the procedure using your own words or using your own logic. Okay. And with that, I'll end the course. Again, sorry for not being able to give the course in person. Again, due to time constraints today, I don't have a Korean version for you. So just listen to the English content again carefully, and you'll probably be able to follow everything. Okay? So I'll see you all soon.